Okay, so we need to continue on with our discussion about energy. And in the next section, what we're going to do is we're going to look at how energy is actually converted, or talk a little bit more about this in depth. We've actually talked a little bit about how that can happen, but we haven't looked at that completely in depth. Now, energy conversion happens, and we look at this because energy does become more noticeable as it transfers from one type to another, or as it is transferred from place to place. This process of changing our energy from one form to another is called energy conversion. And sometimes this actually happens in a series of steps, so I'll actually have multiple conversions of energy as I do this. And we're going to actually look at this through an example of something very simple in striking a match. So when we hold the match in our hands, the first thing that happens is that our muscles actually use the chemical energy inside of those cells to help us to strike the match on the side of the box. So the muscles contain the energy, and it actually gives some of its energy, it transfers some of its energy to the match to make it move. Now, friction builds up between the match as well as the box, and what that does is it takes some of the kinetic energy that the muscles have given to the match, and it transforms it, I should say, into thermal energy. So we get a transformation taking place. Now, this thermal energy can become like the activation energy that we discussed a little while ago. And that's what happens. It activates a chemical reaction on the match tip. So it actually releases some of the stored chemical energy at that point. So we get another transformation taking place. Lastly, then that chemical energy that's been released gets converted into thermal energy that we feel as heat, and also electromagnetic energy in the form of light in the flame. So we get another transformation. So as you can see here, a very simple process of striking the match. We actually get 4 different energy conversions that take place. And this happens all the time without us even thinking about it. So as a result, sometimes talking about specific types of energy can get kind of cumbersome when we're actually looking at a particular object or system. So oftentimes we talk about this concept of mechanical energy. Because we get many conversions taking place between potential energy and kinetic energy, we tend to use this. And if you look at our example of the match, we started off with some potential energy in terms of chemicals in our muscles, turned it into kinetic energy, and that kinetic energy then transformed into other types of energy using potential energy as well. So mechanical energy is referred to as the total amount of both potential and kinetic energy in a particular system. So basically when I'm totaling it up, I'm adding them together. So I can actually look at mechanical energy in terms of this following equation. Mechanical energy equals my potential energy plus my kinetic energy. And what that means is that as an object goes through energy conversions, or in the case I have on the screen here, as it travels, its potential energy can convert into kinetic energy and then back into potential energy without changing the total amount of energy. And the 2 examples I kind of want to talk you through are a roller coaster and a swing. If you think about a roller coaster kind of up at the top of a hill, as it comes down the hill, that potential energy, because it's got a lot of stored potential energy due to its height above the ground, that potential energy as the roller coaster moves down gets converted into kinetic energy, because as the roller coaster comes down, the car speeds up. So it reaches its maximum kinetic energy at the bottom of the hill, but that's also when the potential energy is the lowest. Whereas at the top of the hill, the potential energy is the highest, and its kinetic energy is the lowest because it's traveling slowly at that point. Now, usually in a roller coaster system, you come down a hill and then you actually kind of go back up another one. So as you travel up that next hill, as you go up, the car actually slows down, so its kinetic energy decreases. But because you're increasing the height from the earth, your potential energy increases. But the idea here is that the mechanical energy overall stays exactly the same. Now we also have this with a swing. If you think about swinging on a swing, as you go back in the swing, basically when you have that pause point, you are at the highest level of potential energy that you will have because you're at the highest point above the ground. And then as you come down, you speed up, and when you kind of come through so that you're even with the swing set, you reach that lowest point, so your potential energy is the lowest, but your kinetic energy is at its highest. And then as you swing through, you go up again, your potential energy increases, you slow down so your kinetic energy decreases until you kind of reach that pause point at the top, and then you reverse the process. Now, this leads us to the idea of the law of conservation of energy. And this states, because our mechanical energy stays constant, even as those different amounts of potential and kinetic go up and down, we don't get energy that is destroyed. So the law of conservation of energy actually kind of mirrors the law of conservation of mass. Basically, the law of conservation of energy states that the energy cannot be created or destroyed, but it is able to change forms. So as we're swinging on the swing or riding on a roller coaster, we're actually not creating energy or destroying energy, we're simply changing its forms from one form to another. And we can see that through looking at the mechanical energy, since it's the total of both. That mechanical energy number shouldn't change. But we also have different forms of energy other than kinetic and potential. So I think it was important to bring in this idea of the law of conservation of energy. Now, believe it or not, if you think back to the beginning of our unit where we said that everything in the universe is made up of matter and energy in combination with each other. Well, actually there were some scientists that were working with this whole idea of matter and energy and actually discovered that matter and energy are actually the same thing. And that sounds kind of weird because we know we can hold matter in our hand, but we know we can't really hold energy in our hand. We kind of discussed that at the beginning of the unit. But people who were working on the atomic bomb in World War II, it was called the Manhattan Project, actually discovered that in fact mass can be converted directly into energy, and if we can do that, then we should be able to also convert energy into mass. And this is where Einstein comes into play. He actually found out the relationship between energy and mass. And so his formula is E equals mc squared, where E represents your energy. M, of course, is your mass. Now remember that needs to be in kilograms. And C is the speed of light, which is 300 million, meters per second. That's pretty fast. Basically what Einstein found is that when we undergo nuclear reactions such as fission or fusion, we actually destroy a little teeny piece of mass. And that's why atomic bombs, nuclear bombs, and nuclear reactors generate so much energy. What they are doing is they're actually taking a very teeny tiny piece of the atom and turning that little bit of mass directly into energy. Now this little bit of mass is very small. It's smaller than even an electron, which is, if you recall, we said had a mass essentially of 0. So what we are saying with energy mass, if we take mass and we actually do destroy it, what we do is we create and release energy. So we're really not destroying it, we're just converting it. We're changing mass from its current form into its energy form. Now this may not seem like a lot, but it actually is. Okay, this is the reaction that occurs on the sun as well as in nuclear power plants. So this is the two different reactions of fission and fusion. And what it does is they take small amounts of mass and turn them into energy. And so that is the equation from Einstein that we learned about and that they use to actually calculate how much energy they're actually generating. The idea is because the speed of light is so large, you don't need a large amount of mass to produce a lot of energy. All right, sorry about that. I was having a little coughing fit there. So what I was saying was it does not need to be a large amount of mass in order to produce a lot of energy for us when we actually do convert mass directly into energy. So let's take a look at an example here. Suppose I have 1 gram of mass and I convert that directly into energy. How much energy would I actually produce? Just to give you an idea about how much mass 1 gram would be, if you take a look at a typical paper clip, it weighs about, or its mass is about 1 gram. Now, I do have to convert my grams into kilograms for this. Actually, I'm going to try to do this here on the screen. Okay, so 1 gram, remember, is equal to 0.001 kilograms, and that's what I need to use for this conversion. So I'm going to take this 0.001 and I'm going to multiply it by my 300 million, which is 3 times 10 to the 8th, and I'm going to square that. So it's going to be a really big number. When I do that, I get 9 times 10 to the 13th, and my unit for energy is still joules. Now that seems like a lot of joules, but most of you probably don't understand exactly how much that is. So what I did was I actually converted this number, 9 times 10 to the 13th joules, for you. And just to give you an idea, joules is a unit of energy, just like calories that we eat are a unit of energy. And we can actually convert them between each other. We'll take a look at that in a little bit, but the idea here is that if I took this little paper clip and converted it to energy, if I converted it into a form that humans could actually use, we get energy from our food. If that was a form of energy that humans could actually use to sustain them, based on the typical requirements of about 2,500 calories per person per day, 1 paper clip converted directly into energy would provide enough energy for 8.6 million people to survive a single day. Now that's a lot of people and that's a lot of energy, just to give you an idea. 1 little paper clip produces and contains within it, if I were to take all of that mass and convert it into energy, I could actually provide enough calories to sustain 8.6 million people. That's quite a bit of energy. Now that does not mean that if you eat a paper clip that you could feed 8.6 million people. That's a different process. What I am saying is if we went and converted all of that mass in that single paper clip into energy, that's how much energy it would produce, equivalent to the energy that 8.6 million people consume in a single day. Alright, so we're going to actually take a look in the next video at some of the science behind some of this nuclear energy.